Wait a moment. I'm going to share my screen here. So we have just learned the definition of the convergence rate, and we have another definition here, and it's about the degree of accuracy. And we have already touched the base of this concepts in the last class. So the degree of precision or the degree of the accuracy, it means that for the quadratic formula, and then the largest positive integer n such that the formula is exact for the x to the order of k, that is the polynomial, the degree of the polynomial. So for examples, we have already learned, investigated into the trapezoidal rule and then the Simpson rule, right? And if you take a look at these two formula, and then we have the error term here, and we have investigated into, if we put in fx, we try to put in several things into this formula, right? And for the first formula, the trapezoid rule, if you put in the, so we have several options here, and then different degrees of the polynomial. This is with the degree of 0, this is with the degree 1, and this is with the degree 2, with degree 3. We try to do some plotting there, and then for the degree 1, degree 0, and then this, the second derivative goes to 0, and then up to, let's try out the x and the x squared. The x is fine because the second derivative is 0 again, which means that this formula is exact for the fx equals to x. And if we try out fx equals to x squared, and then you would get some number here. The second derivative it is 2. And then so we would have error for the quadratic polynomial. And so which means that the largest positive integer for the polynomial, the degree of polynomial, it should be x equals to 1. Not x equals to 1, the degree equals to 1. So we would say the trapezoid rule has 1 degree of precision. And for the Simpson rule, if you take a look at here, the error, we have 4th derivative here, and which means that if you put in up to the 3rd degree polynomial here, and then you would get a 4th derivative 0 here, which means that this formula, this quadratic formula, is exact for the polynomial up to degree 3. And so we say this Simpson rule has 3 degrees of precision. And so let's take a look at here. And today we are going to improve the accuracy of the quadratic formula here. And last time when we are deriving the trapezoid rule, and then we use, so this is our A and this is our B, and then we just do 2 nodal points here, and then this is x1, and then x0, x1, and then do the trapezoid rule, and that's the trapezoid rule. And for the Simpson rule, we have one more point, right? This is the Simpson rule, and this is the left endpoint, right endpoint, and we have we denote this one as the first nodal point, and then we get a middle nodal point here, and then we get a end point here. We use 3 points here to get the Simpson rule. And this time, if we want to improve the accuracy, we can divide the intervals into n subintervals, and then to apply this trapezoid rules to each subinterval, And then we can do the same ideas for the Simpsons rule. Instead of doing three little points or two subintervals, we divide the whole interval into even number subinterval, and then we apply the Simpsons rule to each sub intervals, and that is how we improve the accuracies. We do more small. We partition the A and B into small subinterval and apply the Simpsons rule or trapezoidal rules into the subintervals here. So let's say the first one, the most basic one, that is the composite trapezoidal rule, which means that we divide the interval into. So let me draw it here. So which means that instead of a big interval here, we are going to use. So here we have A and B, right? This is the endpoint, and I'm going to divide this interval into some small interval, and then the first one is x0, still x0, and then we have more subinterval here, and then this is x1, x2, and then we have xn here. And for each interval, for each subinterval, and now we apply the trapezoidal rule, and which means that we are using the trapezoidal rule here to approximate the intervals on this subinterval. So I'm not drawing all the things here, but this is the idea. I divide the interval into the whole interval into the n subinterval, and then we apply the elementary trapezoidal rule there. And so now let's take a look at here. If I divide the interval and then apply the trapezoidal rules here, and then what do we get? So this one is just. So this is the subinterval, and then if you have the A is just the x0, and then the B is just the xn, and this is some rules, some rule for the intervals, and then I'm going to use the sigma sums to denote these things for the simplification, and then so we have j equals 0, and then n minus 1, and then integrate from the xj. And then this one is the hj plus 1, and then which means that we are doing the integrals on the subinterval here, and then we add all these integrals together on n subinterval. And so now for this integral, for this specific small integrals, I'm going to apply the elementary trapezoidal rules we learned before. So we got this. We have this. We have so the elementary trapezoidal rule, which means that we have 1/2. This is something you have already learned from the last class. And the last class we have. This is the trapezoidal rule. The trapezoidal rules we learned from the last class looks like this: FAB, FX, DX, right? And then 1/2 FX0 or FAB. So this is the AB. This is something we learned last class: FA and then plus FB, and then there's a H here, and then we have a return here as well from the last class. And now I'm going to replace the A with the xj, and then replace the B with xj plus 1. And then now I also have one return here for this approximation. So I'm going to, from here to here, I'm going to apply the elementary trapezoidal rule in case you don't know what I'm going to do. and I write out the things here. And this is the trapezoidal rule. And there's an error term from the trapezoidal rule, and that's the negative 112, and then the error is in terms of the second derivative, because Cj and then h cubic. Here, because Cj is in the interval x3 and x3 plus 1. And this is the how we apply the trapezoidal rules to a small subinterval. And so now let's take a look at here. So I'm drawing out the things here. So we have x0, x1, right? And then x2, x3, and then all the way to xn. And then I have xn minus 1, xn minus 2. Let's see what's the first few terms here. We have 1/2 fx0 plus the 1/2 fx1, right? So which means that I have 1/2 here, and then I also have 1/2 here, right? For the first interval. And then for the second subinterval, and then this one is integrating from fx0 to x1, right? And then what is the second interval, the integral? I'm integrating from x1 to x2, right? And then for this one, I have one approximation term here is fx1, and then plus the 1/2 fx2. And which means that I have one more coefficient here for the x1, and then that's 1/2. And then, so now I also have 1/2 coefficients for this one. 1/2 h. And let's take a look at the third one. The third one, we have x2 to the x3, and then with the elementary trapezoidal rule, we have this terms, fx1, fx2, and then 1/2 fx3, right? fx3. And then you will see that I am still adding 1/2 to this point, the x2, and then we have a new 1/2 here for the x3. And all the way down to the, we go to the integral here, the integral here, xn minus 2 and xn minus 1, and then you would get the coefficients 1/2 for here and then 1/2 for here. And if we focus on the integrals on this interval, and then we will have 1/2 for the, we will have 1/2 for this one and minus 1, and then we also have 1/2 for the xn. And what do you see here? We see this. We have the coefficients for the x0 is 1/2, and then for the all the things in between. So here we also have 1/2 here, 1/2 here, and for all the things in between, it's with the coefficient 1, 1, 1, 1, 1. And then the last one is with the coefficients 1/2 again. And that's because we don't have duplicate terms for the x0, and then we also have, we also don't have duplicate terms for the xn. So we have different coefficients here. So I'm going to erase all the things because we have already analyzed how the coefficients looks in the formula. And so now, so if we expand the formulas, we got h, and then 1/2 is for the fx0, and then fx1, and then all the way to the fxn minus 1, and then 1/2 fxn. And so what about the error term? The error term we have here is minus 112, and then I'm going to do the sums for all the constituent here. And are you satisfied with this result?
So here we call this one, we call the first term here. This first term here. This is the first term. And then we call this one is the composite trapezoidal rule. So let me just copy them here. It's h 1/2 fx0. This is the composite version. It's more complicated than the elementary version. We are using all of the nodal points here. What about the error? We have the error looks like this: -112 h cubic, and then n-1, and then j equals to 0. And f second derivative can see j. And let's see if we rewrite this h. We take one h out, and then write it into b minus a divided by n, and then let's see what we have. So we take out one h, and then we got 112, and then h squared, and then we write one of the h with the b minus a, and then divided by n. And divided by n, we can write it into 1/n, right? And then sigma sum n-1, and then j equals 0, and the f second derivative equals j. I am doing this in purpose to rewrite this terms. And I'm going to rewrite this terms to make the formula, make the error terms looks more simple. So this is something similar to what we did in the last class, because we have zeros, we have n cos j here. We don't like this. We want just one common cos on the interval to represent the error. So how can we do this? So now we are going to utilize some basics calculus theorem here to get a common cos here. So here, let's focus on this term. We want to get a common cos for that term. And so how can we do this? So let's see if the function f is second continuous on the interval AB, the extreme value theorems would tell us that extreme value theorem. So in case that you forgot what is the extreme value theorem, and I have some things in the appendix here. So the extreme value theorem is saying that if a function is continuous, and then we will have the maximum point and the minimum points inside the interval. And this is the extreme value theorem. And it also stating the where the maximum point or minimum point locates. It could be at the endpoints, or it could be at the critical points. And this is the extreme value theorem. In the completed notes, I will also include this appendix, so you don't need to copy them the things here. So, but now you just need to know the extreme value theorems tells you that for the continuous function, you can find out the maximum points and minimum points on that interval. And so let's go back to what we have here. We are going to use all the things, two theorems in the calculus to figure out the common cos j, common cos to represent the errors. So extreme value theorems implies that because this is second continuous, which means that it is continuous, itself is continuous, and then the first derivative is continuous, and then the second derivative is also continuous. And so which means that the second derivative is continuous, and then we can apply the extreme value theorems to that second derivative. So the second derivative here arrives is maximum and minimum and the minimum on the interval in the interval AB. So which means that, okay, so we have such things here. We have, and we also have the following relations for the efficacy J, because the J is in the interval, right? And then it's bounded by its maximums on that interval. And then the lower bounds for this function, for this value, and then that's the minimums on that interval. And then this is the second derivative function. And that's because we have maximums and minimums values on that interval. And then we can also bound the J as second derivative that evaluate at the J by its maximums and then the minimum. And this is very obvious things. So now we are going to, so this is for all the J equals to 0 and then 1 to the n. We have several J here. We have n plus 1 J here. Not n plus 1. We have n. This J is vary from 0 to n minus 1. So I'm going to sum up all these different J inequality here. And then I got sum up this inequality. This inequalities for J equals to 0 and then 1 and then n minus 1. And then what I get, so we have n different inequalities here, right? Inequalities. And so for the first terms, I have n, the minimum value. And then for the middle term, I'm going to do the sum, right? And then so for different J equals to 0 to the n minus 1, and then the second derivative evaluate at J. And then for the third term, the upper bound, we have n term here. And then because this is J equals 0 from 0 to n minus 1. And then this is the maximum value. Okay, we got that. And this is the inequalities for the minimum and maximums. So what we are going to do is to divide these formulas, this inequality by n. And what do we get if we divide these things by n? So divided by n, so this one is n, and divided by n, and it's just 1, and then 1 over n. Okay, that's something very nice. Why it is very nice? Because that's what we have here in the middle. This is what we have, and then we also have that terms there, and then we want to transform that terms into one C second derivative, and then C something. And then, so we have this term, and then it is bounded by the minimum of the second derivative, and then it's the upper bound is the maximums of the second derivative on this interval. And how do we change this term? And then we have such an inequalities here. We have the upper bound and the lower bound. And then we know this value is bounded by this two bound. And then how can we say this one equals to second derivative C? Evaluate at some C on that interval. So we need one more theorem here. And that theorem you might be very familiar with. And that's the so here we want to involve the intermediate value theorem here. So in case that you forgot what's the what's the intermediate value theorem? Let's go back to take a look at here. So the intermediate value theorem is stating if the function f is continuous, and then k is any number between the fa and fb, right? Then there exists a number c. So here we have fa, fb, and then we take any values in between the fa and fb. Then we can confirm that there exists a number c, and then the fc equals to that any number k in between. Do you remember this? And then so now we are going to apply this theorems to that point. So we have a minimum value, right? And then which means that we have actually we have a corresponding C1 here. And then the C1 F second derivatives C1, and then it equals to that minimum value. And then this C1 is in the interval AB. And then this is because the extreme value theorem is minimum and its maximums can be achieved inside in the interval. And then for that, the same things happen to the maximums. There is this a C2, and then there is this a C2 inside the interval, and then such that the F second derivative C2, and it equals to these things. So this means that, okay, we have the, this is the, it equals to F2 C1, right? And then it equals to F2 C2, right? Okay, so now by the intermediate value theorems, and then we got there is 6. So we just write it. We assume that the C1 is less than or equals to C2. It could be difference. It could be the C2 is smaller, but we assume that the C1 is smaller. But without loss of generality, and then we can write it in this way. We assume that C1 is the smaller one, and then we can write it into the interval. And there is this C on the interval C1, C2, such that because this one is just one value between the F second derivative evaluated as C1, and then it's between the second derivative evaluated as C2. And from the intermediate value theorem, because this is the value in between, and then which means that there is a C2 inside this interval C1 and C2, and then we have the second derivative, and then evaluate at this C, and then it equals to the 1 and then n minus 1. This is the any values in between that maximums and the minimums, the FC1 the C1 and C2 second derivative. And so we can have one C on the interval, and then it equals to that fixed number. Because the C1, C2 is inside the interval A and B, and which means that this C is inside the interval A and B. So let's say we change the notation here. We say this is cos C. And so that we can make the symbols more uniform. And so here we write the, in this way, we are using the extreme value theorem and the intermediate value theorems. And then we can write the cos J and to we have several CJ there, but now we only have one C, and then this C is inside the interval A and B. And now, so here we can rewrite this ton. So the error ton, it looks like this, right? At the very beginning, this is the error ton. And then, but now with all the extreme values, theorems, intermediate value theorem, we can write the errors in this way. The EH, this is the errors of the composite trapezoid rule. And so now the things looks like this. This time I can change it to the F second derivative evaluate at C, and then for a C in the interval AB. Does that make sense? And this is the error ton. And in this way, we write the CJ. We have n CJ there at the very beginning. But now I have the error ton, very beautiful format. We just have one C in the error ton. And this is how to analyze the composite trapezoidal rule and its error. Any question here? How to apply the extreme value theorem and the intermediate value theorem to get a common C? Okay. H squared.
At the very top, we'll raise the oh,
we replace one H with the B minus A divided by N, so that we can create such this. If you take a look at here, it's just the average for the tons here. Okay, gotcha. Never mind. Okay, so this is the analysis. We use two theorems here to get the common C. And so from these observations, and then we have one conclusions here. This is the trapezoidal rule, and then trapezoidal rule, and then for the node points in between, and then there is a coefficient too. And then for the endpoint, left endpoint and the right endpoint, we have the coefficients 1. And this is our error here, B minus A divided by 12 H squared, and then second derivative C. And it seems that there's not so much improvement here compared to what we have the simple trapezoidal rule. If you just look at the error ton, and then you don't see any improvement here. But if you do the experiment, and then you will see some improvement in this scheme compared to the elementary trapezoidal rule. But I'm not going to do the experiment here, but I'm going to do the experiment for the composite Simpson's rule here. And so next, we are going to apply the same technique to get the composite Simpson's rule. That's we are going to. So we are going to have E1 numbers subinterval, and then from the interval x0 to x2, that is one fixed subinterval here, and then we are going to apply the Simpson's rule here, and then for the x2 to the x4, and then another Simpson's rule, and so forth. So we have the E1 numbers subinterval, and then we are going to apply this Simpson's rule there. And then this n should be an even number. And then we require this to be an even number. And then we divide the interval into the subinterval, and then we apply the Simpson's rules to this even numbers subinterval. And let's see what can we get if we apply such an idea, and then what it looks like in mathematics. So I'm going to split the integrals into several subintegral here. And then it's the E1 numbers subintegral. And then it's x2 to the x4 fx dx. And then all the way to, because we require the n to be E1 number. So the last subintegral should be from xn minus 2 to the xn and the fx dx. And so now I'm going to apply the, so for one common xj, and then to the xj plus 2, and then if we want to apply the Simpson through, and then that would be, so we have 3 points here, right? Xj, and then xj plus 1, and then we have xj plus 2. And then if you remember what we have learned in the Simpson through, the simple one, the elementary simple sum through, and then we have 1/4 here for the first point. And then this is, let me see, am I right here? Not 1/4, it's 1/3 for the coefficients. And then we have 4/3 for the middle point. And then we have 1/3 for the end point here. So the Simpson through, the simple Simpson through, if we apply to this interval, and then we have fxj, and then h/3, and then plus for the middle point, we have fxj plus 1, and then the coefficient should be 4 here. This is the middle point. And then for the end point, we have fxj plus 2, and then once again, we have just 1/3 for this term. So this is 1, if I extract the common factor out. And then for the simple elementary Simpson through, we have the error term here is 1/90, and then f4 eta j, and then h to the 5. And that looks nice. And then we are going to use this simple Simpson through and then add them together. So this eta j, for some eta j, and then in the interval xj, and then to xj plus 2, we have 3 points for each subinterval here, 3 loaded points. So I'm going to summing up. Order n to n over 2 contributions here. This integrals here. So we have xn here, and then x2, x4, and then to the xn. So which means that we have totally n over 2 integrals, and then we write the we apply the simple Simpson through to each subintegral, and then we summing up all the subintegral here, and we get the composite Simpson through here. Simpson through, and it looks like this. So we are doing the integrals from A and B, but we are doing the integrals from A to B, but we have the first A point, and then we give it as the x0 another point, and then for the last one, and then this is x capital N, the xn node point. And if we summing up all the subintegral, and then we get the approximations for this integral, and it looks like this: h/3, and then for the first one we have fa, and then for the E1 nodal points we have the coefficients. This is the fx2j, and then we have the coefficients too. You can double check it, and then you can do the same things as I did in the trapezoidal rule. You assign the coefficients to each nodal point, and then you will find out that for the E1 nodal points, you have the coefficients too. And then what about the odd number point? For the odd number point, you will have this n/2, and then this is the coefficients range, the index range, and then this is it represents the E1, the odd index point, and then we have the coefficients for this odd index terms, and this is the coefficients for that term, and we have some exceptions here. We have the both endpoint here, the FA and then FB, they are the endpoints, and then they just have the coefficients 1. And you can use the same techniques as I did in the trapezoidal rule, the composite trapezoidal rule, to analyze the coefficients here. You just assign the coefficients one by one and then add them together, and then you will get such things. 2 for the even number point, and then 4 for the odd number point. And so that's all the things. Is it all the things? This is just the rules, the quadrature rule. And once again, we need to analyze the errors. So for the errors, we are going to sum up all the things. We are going to sum up 1/90, and then we have H5 here. So this is the error term, and then we are going to sum up all the things. And sum up all the things here, and then it should be, let me see. What do I have the sum here? We have n/2 tons here, and then j equals to 1. Am I right? Yes, I'm right. And so we have f eta 4 and then eta j. I think I am making one mistake here in the notes. It should be, if I am using the same notation here, this one, it should be n divided by 2 minus 1, and then it is starting from 0, right? But it's still the same. We have n/2 ton here. So once again, if we want to write this average into one common eta, and then now you know what to do, right? Apply the extreme value theorem, and then apply the intermediate theorem. So assume that the f is 4 continuous on the interval AB, and then you would apply the extreme value theorem similar to what we have done in the trapezoidal rule, but I'm not going to give you a lot of details here in the class, but I have included all the things in the notes when I post it to the Canvas. But here, the idea is to apply the extreme value theorem and the intermediate value theorem. What we get it is, so let's rewrite this terms in this way. So this terms, once again, what is the h? H equals to b minus a, right? And then divided by n, and then so we have 1/90 and the h4, and h4, and then b minus a, and then let me see, it should be b minus a and then divided by n, and then sigma sum n/2 minus 1, and then 0 equals 0, and then f4, and then eta j. But remember what we did in the trapezoidal rule. We want to get the average of this term, right? And then if you divide the n, and then this is not the average, we have only n over 2 times here. So I am going to divide these things by n over 2, which means that this things equals to 180 and h4, and then this is b minus a, and then this one is n over 2, sigma sum n over 2 minus 1, and then j from equals to 0. And now you would get this one. This one is the average of the F4 beta j, right? And so now you apply the same things to here, extreme value theorem and the intermediate value theorem, and then you would get a common eta for this term. And so now I skip the details in between, but if you apply the value, these two theorems to that average, and then we got a common eta here. And then for the etas, for some etas in the intervals, this is the common eta here to represent the error term. And then this is the in the A and B. So I'm skipping a lot of things here, but the idea is the same, and then the details will be in the post-it notes after the class. And so now we got, this is our, let's get the negative here, negative here, negative here. And then now this is the error term. This is the error term for the composite Simpson theory. So what we get here is the following theorem. It's the composite Simpson theory. And as you can see here, what we have assumed here, we need to assume that this function is fourth continuous on that interval, because we want to apply the extreme value theorem and intermediate value theorem to get the common eta. So now, you know, when you're doing some mathematics theorem, you want to prove something, and then you assume you are using some theorem there, right? And then in that theorem, you are using some assumption. And we have some assumptions on the F here because we use these two theorem. So now in your conclusions, you also need to include this assumption. So this is our assumption. We assume that the F functions is fourth continuous on the interval AB. Why do we have such an assumption? Because in the analysis for the error, we use the intermediate value theorem and extreme value theorem. And then in those theorems, we use such an assumption. So we have such an assumptions here. So this is how we get the assumptions for one theorem. When you use something, and then you need to also include in your theorem statement. This is the composite Simpson theory. This is the quadrature theory you use to approximate the values for the interval. And this is the error. And then from this error term, and then you will see this scheme has the 3-degree precisions. Okay, 3-degree precisions. And then compared to what we have at the very beginning in this class, this is the elementary versions, and now we still have the 3-degree precisions. It seems that we does not change anything, but if we do some experiment in it, and then you will see the change here. So here we have, there's one example here. And then the example is asking us to use the Simpson theory, the basic one, to approximate this interval. And now we also use the composite Simpson theory to approximate this interval, but with n equals to 4. So don't forget that in the composite Simpson theory, we require that the n equals even number, because we have three nodal points on the subinterval. And for the three questions, we are using more nodal points here, and then the n equals to 8. So I am not going to use the hands to calculate all the things, because it takes time. So I'm going to use the code, and then I have already showed the code on the cameras. You can try out this here. It's this, and I'm going to maximize a little bit. Zoom in a little bit, zoom in a little bit. It says it's already zoomed in. Why? So, okay, this is the code. This is the real number, the exact value, and I create the symbols for W, and then I do the integration for that exponential functions on the intervals 0 to 4. And be very careful that if I just print out the real value, and then we will get the exponent 4, and then you don't know the value, right? So one thing you can do in the Python, you want to get some decimal points representations here, and then you can say, you use this function here, evaluate a function, and then you use the function here. This is the real value, and then dot evaluate f, and then you print out again, and then you get the decimals representation here. This is the true value, and then that is do the integration. And from here, I am applying the Simpsons rule, and we are going to use a NumPy package here. And for here, this is the Simpsons rule. This is for the even number of time, we have the coefficients 2. For the odd number of time, and then we have the coefficients 4. Does that make sense? And then for 2 endpoints, we have just coefficients 1 and coefficients 1. And this is the Simpsons rule. And also, I use the polar pair to apply to different Simpsons rule here. For the node points, if we have n equals to 2, and that is the elementary Simpsons rule. And then this is the B questions, n equals 4. And then this is the 3, the question 3, n equals to 8. And then now, if I run this block of code, and then you will see the results looks like this. So for the elementary Simpsons rule, the error is 3 point something. And now if we use more node points, n equals to 4, and then the error decreased to 0.265 something. If you use more node points, it's 8, and then with 8 node points, and then we have a more accurate results, and then that error is 0.018 something, and then you will see the magnitude of the error is decreasing by 10 to 1 order, 2 order. So you can see the decreasing of the error here if you use the composite Simpsons rule by the experiment. But if you just take a look at that formula, the error tone, and then you don't see any change. Does it make sense? Any questions here? And this is the composite rules, and then the idea is very simple. You just divide the interval into sub-interval, and then apply the Simpsons rule and then trapezoidal rule, and then add them together. But with all the analysis here, and then the experiment here, and then we know that, okay, we get a more accurate results, and then that's what we want to learn today. I think that's all the things we have today, and then I promise you I'll give you a review, but we don't have the time. And let me just post it on the cameras. Let me just get a very tidy summary and then post it on the cameras. And also you can use it as a cheat sheet in the midterm exam.有啊，我就发错了，所以我要重新发。
哦，好的，因为我周二没有来，然后我看那个片尾上面一直没有，我以为没有实现。
我上错了，因为上传错了。Hello，
我想问一下，就是确认一下，就是这个地方是从零开始，和其他地方都是从一开始。
啊，是我的错，是我的锅，都是追。等我看看哈，如果是我想想哈，因为这里是 H 一开始，这是一开始啦。
哦，这都是一开始，
对呀、
就是只有这个 arrow
对
term 是
对对，因为你想想，这是 x 0了，对不对？第一个 term 不就 x 2了吗？
哦，
然后这里的话，这不得就 x 0的话就 x 1了嘛，
嗯，
对吧？对吧？对吧？
对，OK。然后就是我看一下，哦，就是这里为什么这里是取的 B，这里是取的开区间的？这个地方是不是开区间有关系吗？
那没关系的，都是你就是可以写 B 区间的，对。
哦，所以这里就是开或者就是都无所谓。
对对对对对。
OK，然后好多问题，有一个第一次作业的，
好啊好啊，哦，就 grading 吗？
对，
我以后应该把那个，哎呀，天呐，我的老天爷，稍等一下，我把这个停了先。